You know, you might think that throwing 100 AI agents at a single problem is the ultimate productivity hack.
Right. The assumption is usually just that more compute, more parallel processing, and, well, more automated brain power will inevitably give you a more robust result.
Exactly. But what if I told you that doing exactly that without the right architectural scaffolding could actually amplify your system's underlying errors by over 17 times?
It's a huge issue.
Yeah.
The reality is we are officially in what the industry calls the age of agents.
Yeah.
But building them requires moving way beyond the myth that more agents is all you need. We have to start applying a rigorous science of scaling, architecture, and design.
Okay, let's unpack this.
Coming to you live from the turning point of history at Vesca. Stay tuned for a bulletin from tomorrow.
Welcome to AI Deep Dive with Beskar. I am Amy.
And I am Adam.
We are your hosts for today. To you, the listener, welcome to the show.
Glad to have you here.
The title of today's deep dive is Make Agents Great Again. We are officially in the age of agents, and frankly, this is a much-needed topic that we probably should have covered earlier.
It really is. And we warmly invite you to share your feedback or, your own agent building war stories in the comments section.
Absolutely. We have a massive stack of sources today. We are looking at dense academic papers mapping out system theoretic frameworks, Google Research's massive January 2026 scaling study, highly practical GitHub repositories focusing on 12-factor agents, and Anthropic's definitive guide to building these systems.
So our mission today for you, the listener, is to basically cut entirely through the relentless industry buzzwords. We want to extract the actual foundational software engineering principles needed to build reliable AI agents.
Right, because we're moving away from those simple single-shot Q&A models to autonomous asynchronous workers that are designed to run for 30-plus hours in the background.
But right now, the design in the industry is incredibly ad hoc. I mean, agents hallucinate, they suffer from context collapse, and they get stuck in these infinite execution loops. Today, we map out the architecture to fix that.
The landscape really has changed dramatically. A year ago, the magic trick was just getting an LLM to output a clean Python script, right?
Or like a boilerplate React component.
Exactly. Now, as of early 2026, the baseline expectation is handing the AI a massive legacy code base, giving it a high-level objective like migrate this authentication system and coming back tomorrow to find it completed, rigorously tested, and deployed.
If we look at the landscape as it stands right now, we are seeing systems operating on entirely different temporal scales.
For sure.
I mean, the Claude Agent SDK is now routinely executing for 30-plus hours on single, highly complex refactoring tasks.
And look at Moonshot AI's Kimi code.
Right, which coordinates an agent swarm of up to 100 specialized agents operating simultaneously.
Yeah.
These are no longer just sophisticated autocomplete engines.
They're persistent, stateful, long-running digital workers. I actually lived through the growing pains of this transition last year.
Oh, yeah?
Yeah. I set up this early autonomous agent to scrape a directory of really messy, unstructured financial PDFs. I wanted it to normalize the data and dump it into a Postgres database.
Sounds straightforward enough.
Right. I thought I had given it the right tools and a solid system prompt. I left it running over the weekend.
Oh, no.
Come Monday morning, I had a $500 bill from OpenAI.
Let me guess. Infinite loop.
Exactly. The agent encountered a corrupted PDF, and instead of failing gracefully, the unstructured React loop just kept retrying the same flawed text extraction API call tens of thousands of times.
Blindly trying to force a result.
Yes.
That specific failure mode is incredibly common, and it stems from a profound architectural misunderstanding.
How so?
Well, until very recently, developers have essentially been slapping external effectors like web browsers or database clients directly onto foundation models without any rigorous systems theoretic foundation.
Right. They treat the raw language model like a complete brain.
Exactly, rather than recognizing it for what it actually is, which is just the language and reasoning center of a much larger required system. Jan LeCun recently formalized this problem beautifully in the sources we reviewed.
Oh, the 5 major failure modes that plague current agentic designs.
Yes.
That model is the perfect framing device. Let's dig into those 5 failure modes for you guys listening, because anyone who has tried to put an agent into production has hit the wall on at least 3 of these.
For sure. So the first failure mode is poor world modeling.
Meaning the agent fundamentally misunderstands the environment it's operating in.
Right. It might not grasp that a file system is hierarchical or that a database requires a specific connection state before querying. It just lacks an internal representation of the system's physics.
Which leads directly into the second mode, which is cognitive and decision failures.
Yeah, this is a big one.
An LLM might be exceptional at fast pattern matching, but it falls apart at rigorous long-term logical planning.
Because if a task requires 30 distinct sequential steps, the agent often loses the plot by step 8.
Exactly, forgetting the overarching goal, because the attention mechanism in the context window just gets completely diluted by the intermediate steps.
Then you have the third mode, which is execution errors.
That's where it formulates a good plan but fumbles the tool usage, right?
Precisely. It hallucinates an argument in a JSON payload, or writes a SQL query with a syntax error, and because it lacks a robust error handling layer, that single syntax error crashes the entire autonomous loop.
Just like my PDF scraper.
Exactly like your PDF scraper.
So the fourth failure mode is learning and governance issues. An agent out in the wild encounters new information, but it has no mechanism to adapt without suffering from what they call catastrophic forgetting.
Where updating its strategy accidentally overwrites its core instructions.
Right. It also touches on governance. Without strict guardrails, an agent might decide the fastest way to solve a server storage issue is just to delete the production database.
Which you obviously do not want. Finally, the fifth failure mode is collaboration breakdowns.
This happens when developers try to solve the first 4 problems by just adding more agents to the mix.
Yes, and the agents misinterpret each other. They talk past each other, get trapped in communication deadlocks, or just bloat each other's context windows with irrelevant chatter.
So to fix all of this, we have to stop thinking of AI as generalized magic and start treating it as deterministic software. But before we get into the heavy system theoretic architecture, we need to calibrate our terminology.
Calibrating terminology is essential. Every platform has its own vocabulary for roughly the exact same concepts.
Let's break it down for you. Think of foundation models, systems like DeepSeek, Kimi, Qwen, GPT 5.3, or Claude Sonnet 4.6 as the brains.
Right. These are the reasoning engines. Checking them is called inference. But the critical bottleneck isn't usually the model's inherent intelligence.
It's context engineering.
Exactly. The information you feed the brain is the context. Tokens are the smallest unit, like alphabets, and prompts are the sentences. Engineering this so the model doesn't get confused is crucial.
And context engineering for an advanced audience isn't just about writing a clever system prompt. It is about aggressively managing the token budget.
If you stuff a 128K context window with massive blocks of raw, unparsed HTML just because the models can read it, you are actively degrading the model's attention mechanism.
The model starts skimming. It misses the needle because you purposefully buried it in a haystack of your own making.
Context window pollution is the #1 killer of agent reliability. This is why modern development has heavily pivoted toward the concept of skills and isolated subagents.
Let's use an analogy. If you have a specific set of instructions that work really well, say a security audit, you group them into a skill.
In modern environments, this is quite literally saved as a modular file, often named skill.md.
Right. It contains the prompt templates, the required JSON schemas for output, and specific tool definitions. You do not inject that massive block of text into the main orchestrator's context window.
Instead, you create a subagent. This is essentially a sub-process with a completely pristine, isolated context space. It only loads the skill.md file, and the specific code diff does its job, outputs a structured JSON response, and terminates.
So the primary orchestrator only ingests that final JSON, keeping its own context window clean.
Exactly. The primary orchestrator triggers these subagents via tool calls.
But how do these agents safely interact with the outside world? This is where MCP, the Model Context Protocol, has completely changed the game.
MCP is essentially the universal open standard USB plug for AI models.
Before MCP, developers were writing custom middleware for every single tool. If you wanted your agent to talk to Postgres, you had to write a bespoke Python script.
MCP standardizes this. It provides a secure client-server architecture where the host application can dynamically discover and connect to external data sources without exposing raw credentials to the model itself.
That isolation is key. And actually, if you're feeling overwhelmed by all this context engineering, subagents, and MCP configurations, You should really look into Bade.dev.
Oh, definitely.
Yeah, Bade.dev essentially abstracts away all of these complex orchestrations for users who are just starting out with AI or trying to scale. It works seamlessly alongside these tools. So if you think your AI is not doing a good job or you're hitting that quality wall, try Bade.dev. It handles a lot of the heavy lifting.
It's a great resource. But all of this discussion brings us to a vital philosophical distinction emphasized in Simon Willison's review of Anthropic's new engineering research.
And that distinction is you probably shouldn't be building an agent at all.
Right. This is perhaps the most important architectural decision a technical founder will make. Anthropic makes a very strict delineation between workflows and agents.
Workflows being systems where multiple LLM calls are orchestrated together using predefined, hard-coded deterministic paths.
Yes. You, the developer, dictate the exact control flow using traditional code.
But wait, if we are rigidly forcing the LLM down a hard-coded path using traditional software engineering, aren't we just writing traditional software? Where is the AI advantage?
The advantage is that the nodes within your hard-coded path still require deep semantic understanding. You still need the non-deterministic reasoning of the LLM to parse a messy customer email and determine its sentiment.
Ah, I see. But you want deterministic routing to handle what happens after that email is categorized.
Exactly. You don't want an AI deciding how to update your billing database. You want a standard SQL script triggered by the AI's classification.
That makes perfect sense. So what do those deterministic workflow patterns look like in practice, according to Anthropic?
They identified 5 highly effective patterns. First is prompt chaining, where a task is broken into sequential steps, and the output of one LLM call is programmatically piped as the input to the next.
Second is routing, where a fast, lightweight model acts as a triage layer, categorizing an input and directing it to a larger model only if necessary.
Third is parallelization. If you need to evaluate a document against 10 compliance frameworks, you don't do it sequentially. You fan out the task to 10 separate LLM calls simultaneously.
And then a programmatic aggregator synthesizes the results.
Right. Fourth is the orchestrator workers pattern. This is a more dynamic parallelization, where a central script determines how many workers to spin up based on input size.
And the fifth is the evaluator optimizer loop, crucial for coding tasks.
One model generates code, and a separate model critiques it against a rubric. The original model refines the code based on the critique, looping until it passes.
Notice what is completely missing from all 5 of those workflow patterns: autonomy.
Exactly. In a workflow, the human developer has hard-coded the loops, the routing logic, and the retry limits. Agents, in Anthropic's strict definition, dynamically direct their own processes and tool usage.
Which is why the takeaway for you listening is to aggressively default to workflows. Unnecessary agency introduces compounding points of failure.
Start with a prompt chain. If that gets you 90% reliability, you are done. Only upgrade to a fully autonomous agent for open-ended, highly unpredictable problem spaces.
Okay, so let's assume we are operating in one of those unpredictable spaces. We are building a site reliability engineering agent that needs to independently diagnose and fix live server outages.
High stakes.
Very high stakes. We must build an autonomous agent. How do we build it so it doesn't immediately crash, burn, or delete the production cluster?
This brings us to a fascinating framework from an Artsiv paper we reviewed, detailing agentic design patterns. The researchers argue we have to completely abandon the concept of the LLM as a monolithic brain.
Instead, we must construct a system-theoretic framework that deconstructs the agent into 5 distinct interacting functional subsystems.
This maps perfectly to how we build microservices. Let's break down these 5 layers. Layer 1, sitting at the innermost core, is the Reasoning and World Model, or the RWM.
The RWM is the cognitive center. It doesn't execute code or parse raw API responses. Its sole job is to maintain an internal representation of the system's current state.
It holds the overarching goal in its active memory and directs strategic behavior. It decides what needs to be done next, not how to do it.
Surrounding that core are the operational interfaces. Layer 2 is perception and grounding, the PG subsystem. Think of this as the agent's sensory filtering layer.
If the agent executes a database query and gets back a 50,000-line CSV file, you do not pipe that raw CSV directly into the RWM's context window.
That would pollute everything.
Exactly. The PG subsystem takes that raw input, filters out the noise, structures it, and turns it into a highly compressed, reliable percept. It protects the core's token budget.
Layer 3 is action execution, the AE subsystem. These are the effectors. When the reasoning core decides, I need to restart the payment gateway container.
The AE layer takes that abstract intent and translates it into the actual syntactically perfect Kubernetes command. It acts as a safety buffer.
Then we have the optional but increasingly critical fourth layer, interagent communication, or IAC.
This is the social interface. If your agent needs to hand off a task to a specialized database tuning agent, the IAC subsystem handles the peer-to-peer protocol.
It ensures the payload is formatted in a standardized JSON schema, preventing those collaboration breakdowns LeCun warned about.
And finally, layer 5, encapsulating the entire architecture, learning and adaptation, or the LA subsystem.
The outer shell. Its entire existence is dedicated to observing the performance of the inner layers.
If the agent repeatedly fails a specific task, the LA subsystem analyzes the execution traces, figures out the failure point, and dynamically updates the agent's internal instruction set.
So it actually learns from the failure. What makes this 5-layer framework actionable is that the researchers derived 12 specific agentic design patterns, or ADPs, from it.
These are structural, reusable solutions to recurring agent design problems.
Let's extract the most powerful patterns for our listeners. We have to start with the integrator pattern, which sits right inside that perception and grounding layer.
The integrator acts as a ruthless validation pipeline. Say your agent uses a web search tool to find documentation. Before that retrieved text is allowed anywhere near the reasoning core, the integrator intercepts it.
It checks the data for formatting, relevance, and potential hallucinations. If the data is corrupted, it rejects it and forces the search tool to try again.
Moving inward to the reasoning core, we have the selector and planner patterns. An unconstrained LLM will often try to solve a massive problem in a single monolithic tool call,
Which almost always fails.
The planner pattern intervenes by forcing the agent to decompose a high-level goal into a strict, manageable, directed acyclic graph of subtasks.
It has to outline step 1, step 2, and step 3 before executing anything. And the selector pattern dynamically manages these subtasks, prioritizing them based on shifting context.
Over in the action execution layer, we have the tool use pattern. It acts as a proxy or adapter for secure external tool invocation,
Ensuring the payload is validated against a strict JSON schema before the API is actually hit.
And looking at the overarching system, we have the controller pattern. This sits entirely outside the main execution loop.
It acts as an asynchronous observer, continuously monitoring the agent's behavior for ethical value alignment and safety guardrails.
If an agent tries to execute a shell command that includes a hard delete, the controller intercepts and terminates the process immediately.
But the pattern that represents the biggest leap forward is the reflector pattern, sitting in the learning and adaptation layer. This enables true causal learning.
Think back to your $500 OpenAI bill.
Oh, please don't remind me.
Well, if your agent had a reflector pattern implemented after the third failed attempt to parse the corrupted PDF, the reflector would have stepped in.
It would have analyzed the stack trace, recognized the looping behavior, and deduced why the parsing failed.
Exactly. And then generated an actionable insight, injecting a new rule into the agent's working memory. Do not attempt to parse encrypted PDFs.
The agent learns from its mistake in real time. To really crystallize this, the researchers did a case study on the famous React framework.
React was the absolute gold standard for agents a couple of years ago. It relied on a simple loop: thought, action, observation.
But raw React is architecturally fragile. It relies entirely on the LLM's transient short-term memory.
If a task requires 40 steps, by step 30, the context window is filled with old observations. The model forgets its original objective and starts hallucinating.
But by applying these agentic design patterns, you can salvage the React loop. You add the integrator pattern to validate every single observation.
You implement a recorder and retriever pattern to externalize state management. Instead of keeping all past actions in the active window, the recorder archives them to a vector database,
keeping the active token count incredibly low. And you add the reflector pattern, so when an action throws an error, the loop pauses, analyzes the failure, and updates its approach.
By layering these patterns, you transform a fragile, infinite loop into a robust system capable of running for days.
So while the academic view provides the blueprint, the real friction happens when developers try to actually write the code.
Right, let's pivot to the bare metal developer perspective. Specifically, a phenomenal GitHub repository from an engineer named Dex titled the 12 Factor Agents.
DEX works heavily with sauce builders who are trying to put AI into production. And DEX identified a massive industry-wide phenomenon called the 80% quality wall.
The 80% quality wall is the bane of current AI startups. A team builds a prototype using a high-level orchestration framework. In the demo, it looks like magic.
But when they deploy it to production and try to get it from 80% reliability to the 99% required for enterprise software, they hit a brick wall.
They realize the high-level framework is hiding far too much of the underlying execution. They dig into the logs and find opaque, non-deterministic loops.
They can't debug it. They eventually realize they have to rip the entire framework out and rewrite the agent infrastructure from scratch.
Dex points out a crucial historical oversight. 20 years ago, back-end software embraced DAGs, directed acyclic graphs. Tools like Airflow forced developers to structure code so data flows predictably.
But when LLM agents became popular, the AI community collectively threw the DAG out the window.
The attitude was, we don't need predictable flows anymore. The AI is autonomous.
Just give it a bag of tools and a while loop and let it figure out the path.
And as Dex argues, abandoning the DAG was a profound mistake for production software. An agent in production isn't a magical brain. It is mostly just deterministic software wrapping a non-deterministic inference engine.
The 12-factor agents principles bring hardcore traditional software engineering discipline back into AI. Let's dissect the most critical rules for you to apply.
Factor 3 is non-negotiable. Own your context window. Dex warns against letting any framework abstract away what the AI is actually seeing.
If you don't own the context window, you cannot debug why the model made a poor reasoning decision. You must be able to log the exact prompt string.
Which leads into Factor 4. Tools are just structured outputs. There is a pervasive misconception that the AI executes tools. The AI has no hands.
It simply outputs a JSON string that matches a schema. Your deterministic Python or TypeScript code parses that JSON and actually executes the API call.
Keeping this strict separation is vital. If a tool fails, it's either the AI generating malformed JSON or your deterministic code failing to handle the API response. You debug them differently.
My favorite rule is Factor 9, compact errors into the context window. This is how you implement the reflector pattern.
When your deterministic code executes a tool and the API returns a massive stack trace, what do? A poorly designed framework just crashes.
But a 12-factor agent catches that error, formats it cleanly, and injects it directly back into the LLM's context window, effectively saying, you requested this tool, it failed with this error, analyze and adjust.
You are leveraging the LLM's reasoning capability to self-heal the deterministic execution failure.
And the most architectural rule is Factor 10, small, focused agents. Do not build a massive monolithic agent with a 100,000 token prompt that tries to handle support, billing, and troubleshooting all at once.
The cognitive load is too high. You build highly specialized microagents, a billing agent dedicated strictly to the Stripe API schema.
The fastest way to get high-quality AI into users' hands is to take small, modular agentic concepts and integrate them into existing deterministic code,
rather than trusting a massive, unconstrained AI loop. Now, speaking of autonomy and the urge to just throw more AI at a problem,
we need to address the elephant in the room. There is an incredibly pervasive myth dominating the industry right now. The catchphrase is, more agents is all you need.
The intuitive assumption is that if one agent struggles, adding a checker agent to review its work and a planner agent to guide it will cause performance to skyrocket.
A team of experts is better than a single expert.
Right. That assumption was just systematically dismantled by a massive Google research scaling study published in January 2026.
They tested 180 different multi-agent configurations across GPT, Gemini, and Claude, and what they found completely upends the current multi-agent meta.
Let's unpack the alignment principle. It states that multi-agent systems are phenomenally powerful, but strictly and only for highly parallelizable tasks.
Like in the finance agent benchmark. The system needs to analyze revenue trends, scrape data on 3 competitors, and parse regulatory filings.
These are distinct subtasks that can be done simultaneously. In that scenario, multi-agent coordination boosted performance by a staggering 81%.
Because the tasks were parallel, the agents didn't block each other, and their context windows remained pristine.
But the researchers uncovered a dark side. They tested these architectures against a benchmark called PlanCraft, which requires strict sequential reasoning.
Where Step B absolutely depends on the flawless outcome of Step A. You cannot compile the code until dependencies are mapped.
When they force multi-agent swarms to handle these sequential tasks, performance degraded by up to 70% compared to a single agent.
70%. Why is a team worse at a step-by-step problem?
Communication overhead. For Agent A to hand off to Agent B, it has to summarize its findings. If it omits a minor detail, Agent B starts with incomplete data,
Plus, their context windows become heavily cluttered with inter-agent protocol chatter instead of the raw data. They exhaust their cognitive budget just trying to coordinate.
which leads us directly to that terrifying statistic we teased at the very beginning: error amplification.
The mathematical rate at which a single mistake by one agent cascades and ruins the final multi-agent output.
They tested an independent multi-agent architecture, a decentralized swarm sharing data peer-to-peer without a central validation authority.
In this setup, independent agents working without an orchestrator amplified errors by 17.2 times.
Imagine an agent summarizing a financial report. It hallucinates a single digit, recording a liability as 10 million instead of 100 million.
It passes that payload to the risk analysis agent, which models a highly favorable risk profile, and passes it to the investment drafting agent.
The drafting agent writes a glowing recommendation. The final output is completely untethered from reality, all because of one hallucinated zero in step 1.
That 17.2x error amplification is an unacceptable risk. So if you want safety, you need a centralized hub-and-spoke architecture.
In a centralized setup, you designate a single orchestrator or supervisor agent. The specialized worker agents operate in total silos.
They only receive instructions from the supervisor and only report back to the supervisor.
The supervisor acts as a mandatory validation bottleneck. It evaluates the output. By forcing all data through this central hub, error amplification was reduced from 17.2x down to just 4.4x.
You must match the architecture to the task's tool density and decomposability. So how do you actually coordinate this centralized model in code today?
Enter LangGraph Multi-Agent Supervisor. LangGraph provides a library specifically designed for creating hierarchical deterministic state machines powered by LLMs.
A supervisor agent orchestrates specialized workers. How does it pass control without losing state?
It uses handoff tools. The supervisor invokes a strictly typed tool call that formally transfers execution state to a worker's subgraph. The worker finishes and invokes a tool to hand control back.
Let's use a concrete example from the source. You ask the system, what is the combined headcount of the FAANG companies in 2024?
In an older React loop, the agent would try to search the web, hold all numbers in memory, and do the addition, likely hallucinating a sum.
But in the LangGraph supervisor model, the supervisor routes the task to a research expert equipped with web scrapers.
The research expert queries the web, extracts the structured data for Meta, Amazon, Apple, Netflix, and Google, and hands control back.
The supervisor has the raw numbers but knows it shouldn't do the math itself, so it routes those exact numbers to the math expert.
The math expert writes a Python script, safely sums the integers, and returns the verified total.
It is incredibly clean, but when the research expert comes back with all that data, does the supervisor ingest the full search history?
No, LangGraph allows you to configure state output mode. The supervisor can choose to ingest just the last summarized message from the worker, avoiding context bloat.
They even have a forward message tool to pass the worker's exact output directly to the user, saving tokens and preventing the supervisor from accidentally altering the data.
That level of granular control is exactly what the 12-factor principles advocate for.
Let's give you a rapid-fire update on the state-of-the-art as of early 2026, the terminology Rosetta Stone.
First, Anthropic's Claude Code ecosystem. They lean heavily into workflows, plugin marketplaces, and native support for MCP.
Then you have editor-native champions like Cursor running background agents asynchronously in AWS virtual machines.
On the open-weight side, Moonshot AI's Kimi code, powered by K2.5, a 1 trillion parameter model optimized specifically for coordinating up to 100 parallel agents.
And finally, OpenCode, the Switzerland of coding agents, an open-source CLI that lets you mix and match models from different providers within the same LangGraph-style workflow.
Every platform is adopting skills saved as local configuration files, isolated subagents, and deterministic state routing. Vendor lock-in is ending.
You can configure Claude Sonnet 4.6 as the supervisor, Kimi K2.5 for parallel coding, and a local DeepSeek model purely as the code reviewer.
It's the ultimate realization of the centralized architecture.
To summarize this deep dive, we've moved from viewing agents as magic black boxes to understanding them as engineered systems.
We deconstructed them into 5 subsystems, applied the 12-factor principles, and busted the myth that more agents is always better.
Whether you are a hobbyist or an enterprise developer, start simple with workflows, own your context window, and explicitly map your agent architecture to the nature of your task.
I want to leave you with a final thought to mull over. We discussed how open code allows us to mix and match different models in a single orchestrated team.
Right now, you, the human, are the architect deciding which model plays which role.
But if agents can dynamically direct their own tool usage and learn via the reflector pattern,
How long until the supervisor agents start dynamically evaluating hiring and firing other AI models in real time based on live API pricing and task performance?
we are teaching agents how to engineer themselves. What happens when they become better architects than we are?
It's a provocative thought to end on. Please drop your thoughts in the comments. Thank you for joining us on this deep dive. Keep building, and we'll see you.